Hello everyone, this is Kirtana and Bindu. This is our project on implementation of feature extraction using Cortex Altera. What is feature extraction? Feature extraction is mainly transforming the input data into the set of feature. Uh, what we have done is we have chosen Lena image and we have cropped the image, and basically in this image we have taken the corner points. We have chosen it carefully because corner points are the ones which have significant change in the gradient values. So this is the Lena image, and we have chosen the corner points, and we are going to input these we are going to input the matrix which we get from the MATLAB, that is 128 by 128, which is supposedly we are supposed to input 128 cross 128, but because we could not fit it into our C we and Verilog, we have cropped it and taken only 49 cross 49 matrix,
So
and
for
the Verilog
for proceeding ahead, the feature point, in order to get the best feature points, we had to do some research. Like we had to find the threshold value, which is actually the eigen value, and the minimum distancing and the patch value. All these three values had to be found out. This is for the initial trial of threshold of 10, which we are getting the
But you can
clusters,
see a
and
lot of clusters
the
which have been
yeah,
formed.
the features are not
So we
properly
have to
defined.
include minimum distancing
So that's
for
why
this.
we went for more minimum distancing and a different patch size. So we had to go for minimum distancing and a different patch. So when we went for the different patch, and that too we had to go for overlapping patch. Previously we went for non-overlapping. Now we had to go for the overlapping and a different threshold value of 100, wherein we got these features. They are nicely seen, the eyes, they are nicely distanced also. So keeping this in mind, we started to proceed ahead. But inputting this 128 by 128 is so huge, as Kitana told. So that's why instead of resizing the image, we thought of taking the cropped image. That is the image where the most of the features are there. We took the face of the Lena image. We took from there, we went to the gradient. From the gradient is the basic matrix from where we find the eigenvalues. From the eigenvalues, we go for the calculating ABC values, and we got these feature points. Now we know the set of the feature points to be we know the threshold value to be decided, we know the patch, and it has to be overlapped by what extent, and along with
Also,
it,
the minimum distancing has to
yeah,
be 3
minimum
after
distancing.
trial and
So
error.
with all keeping
It will
this
be
in
good.
mind, we went for implementing this module in Verilog through Neos. So we created a Verilog module which would input the data through
Yeah, we would actually input this using C, and we've used using Neos, and the input data will come serially. We have implemented raster scanning in the inputting of data. Once the input data has come, once we catch it in the Verilog module, what we have done is we need to actually find the p-value, that is the corner detection algorithm. We can summarize it using summarize it as such, like the image gradient has to be computed first, that is ix and the iy value, and from the image gradient we also need to find a b c values. Before this we need to finalize the patch, and we have our patch size. We thought which it would be best to take 5 cross 5 patch size. After finding the patch, every patch will have a local maximum value, which is the p value. So once we find p, we need to filter p values, because there will be a lot of p values for every 5 cross 5 overlapping matrix. So whichever is greater than 0, and if A is greater than the threshold, only then we retain the values. So also we retain the corresponding coordinates, and we discard the remaining p-values, which is not the local maximum. So then we arrange all the p-values in the pixels in the descending order, and then we inculcate minimum distancing to avoid the clustering of the points, feature points, like how we just saw. So this is about the algorithm, and we have done a part of it in Verilog, a part of it has been written in C, and and we have used hardware accelerator so that it happens faster. But because of some memory issues, we were not able to interface Verilog and C using Neos. So we are going to show you the Verilog code where we calculate ABC values, and once we calculate the ABC values, we are going to input these ABC values in C, and we're going to show you the output so that we get the feature points and match the feature points with the MATLAB feature points.
So this is the QSys interface which we opened from the Quartus tool. This the interface, as you guys can see, the interface. This is the interface which talks between the Quartus tool and the Neos processor in the DE1 board. So as you can see, this QSys interface consists of clock, Neos, and on-chip memory, and JTAG, UART, and performance counter. And this is the module which we wrote in the Verilog, which is actually going to give us the ABC values, which we will take and give it to the Neos processor through the IO read write statements. Since it's all being interconnected, every module should be given the clock properly and reset. And what we'll do is we will assign the base address, and then we will generate. Yeah, we have to save the changes, and we will generate. So basically this generate command will generate all the various Verilog modules required for the project, so that now our Verilog module in the Quartus can talk to the Neos through the QSys. QSys will be the interface. Once these modules are generated, we can add these modules to the Quartus tool, and from there we can go for the compilation, and then we have to burn the code. Then we have to open the Neos 2 processor, and let's see how it works. So basically this Verilog module is going to send the ABC values. These ABC values are will be in this order. That means since it is in the raster scan, once the patch is getting ready, the value of A will be getting ready, and since the overlap is 2 overlaps, so it will wait for 2 clock cycles, after which the next patch will come. After the next patch comes, it will maintain the same ABC values until a new patch is formed. So these are the ABC values for the 4 different patches. This is only the trial version that we have chosen to explain it to you. These values match the values which come in the MATLAB that I'll show you shortly. Let us see if our files are generated. They are still being generated. Okay, while this is getting generated, let us go back to our MATLAB and let me show you the A values. A of 1 to 10. As you guys can see, the first two values are the patch values which we got from the waveform 13048.
Basically, whatever the MATLAB values have been got and the waveform values have been matched.
Matched, yeah. So after these two values, it will raster scanning will not stop there. It will proceed until it has reached the entire 22 patches in a row. After which it will come to the next row. Sorry, these are the elements. Since for your since we took a short patch of 9 by 9 for this showing of the values, so 9 by 9 has only 4 patches, so 4 patches has 4 different values. So these two values are actually the 23rd and 24th patch value, which you can see in the MATLAB, a of 23 and 24. So these values, they match here. That means the values of A, B, C, similarly B and C can also be displayed along with the dx and dy directions, and these will be the values which we will be giving to the NEOS processor. So our generation is complete. We will close it, and we will add this file. So the generation will generate all Verilog modules, or a simple QIP module will also be stored. So either we can download all the Verilog modules or the QIP values, QIP QIP file. So for now, let us load the QIP file. This is the latest one, and we will open, and we will add this, apply, okay.
Adding the
Then
test bench.
we will go for the assignment editor. There is only one pin and it is all assigned properly. Then we will run the code. This code running takes a long time because it is 49 by 49, 49 by 49
And
image. The size,
yeah, a
we are
lot of
using the frame
complication to
buffer
the.
here, so it takes a long time for this compilation. So that's why we showed the values that this module is going to give through this in this way.
This is basically the output of the Verilog module itself, but it is going to take a lot of time. So this is the output we are showing.
Mm. So since we had the
And
issues
later
with the
on, we're going to bring this ABC, which is the output of Verilog, as input to C, so that we can calculate the remaining values and output the feature points. So
so
this is the C program. Here we have written the code for finding. See, these are the input values of ABC, which we have got from the Verilog code, and we have found all the p-values, sorted array, and everything. And then the final the uh, output is the degree of confidence and also the respective coordinates. So these are the degree of confidence and the coordinates. So actually, if there was no memory problem, then we could have interfaced it and then run it, and we would have got the same output anyway. And this output will now match with the Lena image which we are supposed to get. But because of the memory issues, we were not able to interface it. So we can leave it. We can do that in the future as an improvement in the
so
project.
the all the C values which we got from the C programming, we I inputted into the MATLAB so that I can cross check with the MATLAB values and the Verilog values. So let's run the code again. So now we can see two different images. See the figure 3, it shows the figure which is actually generated by the MATLAB, and the figure 4, these are the values which is
Which,
generated
yeah.
from the C code. As you
And there
can
is some
see,
resemblance, that is the eyes, hair, and the shoulders. The feature points are matching somewhat, but there are a few distortion because we have taken 49 cross 49, and because of the minimum distancing algorithm which we have inculcated.
Yeah, obviously, every time the hardware output and the software output is not going to be the same, because we have to approximate many things. So this is the best approximation we got. In future, this is only for 49 is to 49. In future, if we use SD RAM, which has got a greater memory size, then we can go ahead and input the entire 128 by 128 image, and then we can do some more modifications in the algorithm so that it can nicely detect the feature point of the software. And that would be our future endeavor. And in this term project, we were able to do until this point. Let us see what is the status. It is only 2% and it is 3 minutes. It is going to take a lot of time. And yeah, anyway, whatever time it takes, the output is going to be this only, so which we already showed it to you. And yeah, so this is the ideal value, and this is the value which we get from the C programming. And thanks a lot for your time.